Okay, welcome to the lecture of linear algebra. Today, in this lecture, we'll talk about dimensions of a vector space. So, along with this topic, we will also study uh, the rank of a matrix, which is a very important topic in linear algebra. Okay. So, continuing from the last lecture, we have already studied the coordinate systems in vector space. Now, uh, a vector space V, we know that with the basis B, V with a basis V containing n vectors is isomorphic to Rn, right? So we gave in the last lecture a few examples of the isomorphism. Um, so this number n is basically is an intrinsic property of the space, which is called dimension of V. Okay, and this dimension of V actually does not depend on particular choice of bases. Okay, so there could be different bases which having the same dimension that can span V. So in order to define this, we can say that if a vector space V has a basis B is equals to B1 to Bn, then any set in V containing more than n vectors must be linearly dependent, right? So we know that in a vector space which having the basis of n vectors, so if you add any other vectors or any other collection of n vectors, n plus 1 vectors from the vector space, that set will become dependent. Okay, so now similarly we can very specify this phenomena as a basis of n vectors, then every basis of V must consist of exactly n vectors. Okay, so first thing that you have to remember that the vector space, if it has n basis vectors, so any set in V that basically that is the collection of more than n vectors actually becomes linearly dependent. And the basis, say for example, if you have a vector space and you set you pick n vectors from the vector space which are linearly independent. Now if you want to pick another basis for the same vector space, there you must have at least n vectors, okay, to specify the basis of V, because you can have a different set of basis vectors for the vector space. The only condition that is there is that these set of vectors must be linearly independent. Okay. Similarly, if V is spanned by a finite set of vectors by a finite set, and then we say this is a finite dimensional. This is because this is a finite dimensional. Now and we write this as dim V, right? So it's a dimension of V, and dim V is actually the number of vectors, is actually the number of vectors in basis of V. Okay, now similarly there might be a situation if V is not spanned by a finite set. If V is not spanned by a finite set, in this case V is said to be infinite dimensional. V is infinite dimensional. The only explicit thing that you need to know is that zero vector space is defined by a zero. So it means if a zero space is defined by 0. Okay. So to give you an example on that, about the finite dimensional fields, vector space. Say for example, in the last lecture we covered this thing here, that R of n containing n vectors. Okay. So dimension of R of n is equals to n. So if Rn is a space that is that contains n vectors, then we know the dimension of Rn is n. Similarly, when you talk about the standard polynomial, and which is itself is a vector space, so 1 t square, and these are the bases of that vector space. So it means here dimension of p3 p2 actually p2 is equals to 3. Similarly, because there are 3 set of vectors, and then we can say dimension of p, let's say 3, would be 4, because then there will be 1 t square and t cube. Now similarly, dimension of nth order polynomial vector will be n plus 1, and the space p of all polynomials, right, is infinite dimension. So this is the finite dimensions, okay, and this is the set of all polynomials will be an infinite dimension, okay, because then you require infinite number of polynomials here to actually express any polynomial p. Similarly, we can say let's say h is equals to span of v1 and v2. v1 is equals to 3, 6 and 2, and v2 is equals to -1, 0 and 1. So we know that this is nothing but a plane in 3 dimension, that is a plane, and the basis for h we know that will be v1 and v2, because span is actually spanning sets also form the basis as long as they are linearly independent, which they are in this case. We can see that so since v and v2 are independent, it means we can say that dimension of h in this case is 2, because there are only 2 linear independent set of vectors. To further see that, let's say we have to find the dimension of the subspace H, which is a minus 3b plus 6c plus 5a plus 4d, b minus c minus 2c minus d, and 5d, right, such that a, b, c, d in R. Okay, so we can write this one in a form which is we already know, quite convenient to us, that which is comes out to be 1, 5, 0, 0 into a. Similarly, plus minus 3, 0, 1, 0 into b, plus 6, 0, minus 2, 0 into c, plus 0, 4, minus 1, 5, d, right. So here we know that now this is a vector v1, this is a vector v2, this is a vector v3, this is a vector v4, Now what we have to check is, are they really they are linearly independent or not. So uh, from here we can see that uh, so to check for the linear independence, what we have to do, simply check is if they form a trivial solution or not. Yeah, to do that, right, uh, we can we can see first of all that v1 is not a multiple of v2. Similarly, v2, if you look at v1 and v4 are not each other's multiple. The thing here is v1 similarly v1 and v3 are not multiples of each other, but v2 and v3 are multiples of each other. So thing is, we may discard v3, and then when we discard v3, then we have the basis vectors as v1, v2 and v4. So there are only three interior independent vectors, so dimension of h in this case is equals to 3. Now there could be further subspaces of a finite dimensional space. All of the examples that we covered so far are of the subspaces are actually examples of the subspaces of finite dimensional space. So if the H be a space of a subspace of finite dimensional vector space, so it's V, right? So the possibility that you can have on the dimension of H is less than dimension of V, right? So for that you have just covered this example here. Say for example this scenario, so we got these vectors exist in R4, right? But the dimension of the subspace that you are getting is actually 3, right? So this statement is true, the dimension of H is less than dimension of V. Similarly, if we say let V be a p-dimensional vector space, in which we say p is greater than 1, any linear independent set of vectors of exactly p elements in V is automatically a basis of V. Okay, now what it's saying here is that if V is a p-dimensional vector space, so if you choose any p elements in V which are linear independent, they could form the basis of V. For example, to give you an example on that, say like this was previously we were doing for the standard basis, which was 1 0 and 0 1, right? Now similarly you can have a standard basis which so it's a two-dimensional vector space. So I can pick any two vectors which can actually form the basis of this vector space. Now this could be a vector space. Okay, now say for example, and this could be, okay. Now you can see here you cannot write one in the form of other, right? So it means they are linearly set of independent vectors. So it means these are also can serve as the basis of this two-dimensional vector space. Now coming back to again the matrices that we are dealing with. So as we already defined, if there is a matrix A, right, we have two kind of spaces that is associated with this A. One is called the null space of A, and one is called the column space of A, right? And we know that the null space A, the dimension of the null space of A, as from earlier lectures, is the number of free variables, is the number of free variables that you have when you solving for for ax equals to 0. Okay, and similarly column space of A is nothing but the number of pivot columns. Okay, the dimension of that is the number of pivot columns in A. Okay, so effectively the number of free variables are actually equal to the number of non-pivot columns, because that only that rows actually corresponding entries will actually generate the free variables. It are the number of non-pivot columns. So the dimension of you can write this as we can generalize this to a point that so number of pivot columns in A for the column space of A, and null space is actually the number of free variables or number of non-pivot columns. Okay, now let's do an example and we find the dimension of the null space and the column space of matrix. Let's say A is given by the following matrix, which is -3, 6, -1, 1, -7, 1, -2, 2, 3, -1, 2, -4, 5, 8, and -4. Right now, if I reduce that equation here by moving this one up top and bringing it down here, so effectively I can write this as 1, -2, 2, 3, -1, and of course this is 0, and because we augmented for the null space, for the null space you have to solve for ax equal to 0, remember. So second one could be -3, 6, 2, -6, 3, -1, 1, -7, 0, and 2, -4, 5, 8, -4, and 0. Okay, now when you row reduce that matrix, you get here is 1, -2, 2, 3, -1, and we got here 0, 0, 1, 2, -2, 0, 0 here, and then you get here is 0, 0, 0, 0, 0, and 0. Okay, now we can see here that this last row is 0, and actually we got 1, 2, 3, 4, 5 variables, of actually 5 variables, x1 to x5, because we are solving for ax equals to 0. Now, so it means that there are 3 variables, 3 free variables, because if you look at this equation from here, actually the only terms that we are getting is x1 to x5 and x3 to x5, right? So x1 and x2 already free, right, and x3 becomes free from the fact that last row is 0. So there are 3 free variables. In this case you can choose them to be x2, x4, and x5. Okay, now this is, it means the dimension of null A, which is dimension of null A, becomes equals to 3. Now if you can see here, the number of pivot columns in this one is 1 and 2, right? So dimension of column space is equals to 5. Okay, sorry, 2. So the question, so now we have understood how we can find the dimension of the null space and the column space. So looking at that, we should answer the following. We should be able to answer the following, right? So let's say V is non-zero finite dimensional vector space. Okay, now you have to tell if this statement is true. So if, let's say, dimension of V is equals to P, and if S is a linearly independent subset of V, then S contains more than P vectors. What do you think? The question is that if the dimension of we know is V is the vector space is P, and F is a linear independent subset of V, which is S is a set of vectors that contains the vectors from V which are linear independent, then S contains more than P vectors. Okay, is it true or false? So I'll give you some time in the video to think about it before you make up your mind. The obvious answer is false. Okay, because dimension of V is P, so any vector more than P vectors in S actually will be a linearly dependent one, right? So S, if since already told that S is only a linear independent subset of V, it means there could be no more P vector in that S. Okay, and from the very first theorem here, that he said that the vector space V has a basis B, then any set in V containing more than n vectors must be linearly dependent. So in this case, if dimension is P, right, so there could not be more than P vectors in the basis actually in S that can be linearly independent. Now the second part is if, say, S is the sector vector that spans V, and if T is a subset of V, then that contains more vectors than S, then T is linearly independent. So the question is that if S spans V and if T is a subset of V, right? S is a set of vectors that spans V, so actually you can think of them as the basis vectors, and if T is a subset of V, there T is a vector that contains more vectors than S, then T is linearly independent. Okay, now this statement is true from the fact that that S contains what you're saying is a basis of V, right? And now because T is a subset of V, right, then actually T contains more vectors than S prime, and it means that from the very first theorem these are linearly dependent. Okay, now the statement I wrote was wrong. Actually the question was then T is linearly dependent, not independent, because if it is independent then this is false. If it is dependent then it's true, because again from the same fact that if S is the basis of V, right, now any other set that contains more vectors than S, right, then it's bound to be linearly dependent. Okay, if the number of vectors are less than S, they can be linearly independent, but actually you have to check for it. But if you say, because we are saying T is a subset of V that contain more vectors than S, then T is linearly dependent, then that is true, because any more vectors that are greater than the number of basis vectors will actually become linearly dependent. Okay, that's what the statement says. Another important concept that is related to the dimension of the matrices and the vector spaces are the row space. And the row space, so if A is an M cross N matrix, right? We know that each row has n entries, and if you think of the vector, say, let's say 1 2 5 6 4 3 2 1 2 1 2 0, right? Now if you think of this one as a row space, it means here in the column side we have got 3 entries, right? But on the row side we actually have got I've got 4 entries. So for an M cross N matrix, we've got M entries in the column and N entries on the actually row side. So it means the set of similarly we can define, as we have defined the column space of A of this matrix A, we can define the row space of this matrix A, which is nothing but the linear combinations of all of the row vectors, right? So the set of all linear combinations of the row vectors is called row space of A, and generally is noted by and is row of A. Okay. Now you can express this row A as something like this, as row A as equivalent to column of A transpose. So it means you take an A transpose and then you find the column space of that A transpose, that is nothing but equivalent to the space of row A. Okay. Now to give you an example on that, let's say A is minus 2 1 3 1 minus 5 3 11 7 8 minus 5 minus 19 minus 13 0 1 7 5 minus 17 5 1 3. So we can see here the row vectors are the 5 row vectors, which are minus 2 minus 5 8 0 minus 17 R2, as similarly you can have that. Similarly you got R4 vectors, which is 1 7 minus 13 5 and minus 3. Okay, so the row space of A is nothing but span of R1 R2 R3 and R4. Okay, now similarly, as we have defined the spanning set theorem for the column space, we can also define the spanning set theorem for the row space. So if all these row vectors are linearly independent, right? So we can use all those for vectors to span the vector row space of A. But if any of the row vectors are dependent, right, so we can remove that vector and replace it and remove that vector and write the vector row space as the span of the remaining vectors. Similarly, there is also associated property of row spaces, that if two matrices A and B are row equivalent, we know that, then their row spaces are the same. So if B is in echelon form, the non-zero rows of B form a basis of the row space of A. So if B is in echelon form of A, B, let's say if B is an echelon form the non-zero rows of B forms the basis of row space of A as well as B. So two matrices A and B, if they are row equivalent, then their row space is the same. Okay, and if B is an echelon form of A, actually the non-zero rows of B form the basis of the row space of A as well as B. So you can use it for both. Okay, now let's do an example to illustrate to find the row space and the column space of all those of a general matrix. So if I say take the again that matrix -2 1 3 1 -5 3 11 7 8 -5 -19 -13 0 1 7 5 -17 5 1 and 3. Okay, so we've been asked to find the basis for the row space, and null space. Okay, now to want to find the basis for the row space, so what you have to do is reduce A to echelon form, and when we reduce that A to echelon form by moving this second row to the first row, so it becomes 1 3 -5 1 5, and we got here is so you keep -2 -5 8 0 -17 -17 or 7 17, you have 3 11 -19 7 and 1 1 7 -13 5 and 3. Okay, so we can reduce it to echelon form, and first row, multiply the first row with 2 and add it into a second row, multiply the first row with 3 and subtract from the third row, and multiply the first row, subtract the fourth row with the first row, right? So if you do that and do all these kind of operations, what you eventually get here is, and similarly from when you left with this thing here, then you can do the subsequent rows and elements, and you are left with 1 3 -5 1 and 5 0 1 -2 2 -7 0 0 0 -4 20, and what you get here is 0 0 0 and 0. Now you can see here the first three rows are actually non-zero, so we can say that they can form the basis of the row space of A, right? So if I say this as R1 R2 and this R3, the row of A is nothing but equals to span of R1 R2 and R3. Okay, so and these are actually the basis of also the row space R1 R2 and R3. Now for the column space, right, so what we have to do simply is to look for the number of pivot columns in A. So what you find out that number of pivot columns in A, with the pivot columns is actually 1 2 and 4 and 1, so the number of pivot columns is actually the dimension of the column space, and these can also serve as the basis for the corresponding basis for the column space. But remember, from the last lecture we already told you that you have to be very careful in deciding the basis for the column space, because if you reduce in echelon form, the matrix in echelon form, you might not be able to span if you use this reduced echelon form or echelon form vectors as the basis for the column space, you will not able to span the complete column space of A because of the 0 entries, right? So the correspondingly column 1 2 and 4 are pivot columns. So we can go to the vector A and take 1 2 and 4th column as the basis of the column space of A. So the basis for column space of A is nothing but equals to 2 1 3 1 and minus 5 3 11 7 and 0 1 7 5. Okay. Now, in order to find the basis for the null space, what we have to do is to take this matrix and reduce it to reduce echelon form. And when we reduce it to echelon form, the matrix, this matrix comes out. We write this again here. You further reduce it to something like this: 1 0 0 0 0 1 0 0 1 minus 2 0 0 0 0 1 0 and 1 3 minus 5 0. Okay. Now we can see here this is kind of equivalent to the following equation, which is x1 plus x3 plus x5 equal to 0, the first row. This one is x2 minus 2x3 plus 3x5 equals to 0, and the last one is x4 minus 5x5 equals to 0. So we can see here from that very fact that okay, you can write this as nothing but x1 is equals to minus x3 minus x5, and x2 is equals to 2x3 minus 3x5, and you can write x4 is equals to 5x5. And you can see here there are two free variables, which are x3 and x5. So they are, because we are free to choose their values, so you can simply have this basis for null space of A as from this equation as nothing but equals to x1 x2 x3 x4 and x5, which is nothing but equals to minus x3 minus x5, 2x3 minus 3x5, and we got here x3, we got here x5 x5, and x5 is x5, right? So this comes out to be again minus 1 2 1 0 0, which is x3, and plus minus 1 minus 3 0 5 1, which is x5. So these vectors are the basis of null space of A, which are given by the following here: minus 1 2 1 0 1 and minus 1 minus 3 0 5 and 1. Right, now we can see here that the dimension of the column space is 3, and dimension of the null space of A is actually 2. So which comes out to be 3 plus 2, which is equals to 5. And you can see here okay. Now similarly we can now define the rank. We explicitly define the column space, dimension of the column space. The rank of A is the dimension of column space of A. So in this case, in the last example, the dimension of the column space was 3, right? And similarly, we know that the row of A is equals to column A transpose, right? So is the dimension of the row space of A is the rank of A transpose, right? So we can say that the dimension of of row space of A is the dimension of, is actually the rank, because rank is the column space rank of A transpose. Okay. Now generally the rank theorem states that the dimension of column space and the row space of M cross N matrix A are equal. Okay, so it says that the dimension of, it's a very important, the dimension of the column space and the row space of an M cross N matrix are equal. Okay, so generally that means the rank of A is equals to rank of A transpose. Okay, and also the dimension of the rank of A also equals the number of pivot positions in A, which is the column space, dimension of the column space. So in this case we can say the rank of A plus dimension of null of A is equals to n. Rank of A is the dimension of the column space of A, and column space is nothing but a number of the pivot columns, right? Now the number of pivot columns, for example in this scenario, is 3, and number of non-pivot columns in this scenario are 2, which are this one and this one, right? So the dimension of null space is actually 2. So we got 3 plus 2, which is equals to 5, and see, this matrix is actually 4 cross 5 matrix, or M cross N. So N is the number here. So in this case rank of A plus dimension of null of A is equals to N. Now we can illustrate this concept by a simple example. Let's say if A is a 7 cross 9 matrix with 2-dimensional null space, what is the rank of A? What is the rank of A? So if A is a 7 cross n matrix, so remember M cross n matrix with 2-dimensional null space, what is the rank of A? So we know that from that formula that rank of A plus dimension of null of A is equals to n. So in this case rank of A plus dimension null of A is 2, n is nothing but 9, so rank of A is nothing but equals to 7. Now another example that we can do is could a 6 cross 9 matrix have a 2-dimensional null space? Now could a 6 by 6 cross 9 matrix have a 2-dimensional null space? So it means what do you think? Now let's say, so it's M cross n, right? Remember, so M is equal to 6 here and n is equal to 9 here, right? So if you look at this formula, then rank of A comes out to be 9 minus 2, which is equals to 7. So rank of A is 7, right? And rank of A is nothing but number of pivot columns in A, right? Number of pivot columns in A, right? Number of columns are there is actually so number of pivot columns in A, so it means God has to have 7 pivot entries, right? But we cannot have 7 pivot entries because M is equals to 6. So it means rank of A, in this case we can say that this statement is effectively not true. So dimension of the column space of B cannot exceed 6 in this case. Okay. So we'll summarize the invertible theorem and we'll talk about so if let A Bn n cross n matrix. So the following statements are equivalent and they are true, right? So first one is the columns of A form a basis of Rn. Similarly, column of A is in Rn. Dimension of column of A is equals to n. Rank of A is equals to n. Null of A should be equal to 0, and dimension of null of A should be also equals to 0. It means if A is an invertible matrix, if A should be invertible, it means is the column space of A should be in Rn, okay, because we know that rank of is actually number of pivot columns plus number of non-pivot columns. So number of pivot columns in invertible matrix should always be same as the number of it should be same as number of n, right? And dimension of column of A should be is n. Rank of A should be n. Null space should be 0, and there should be no free variables for n invertible matrix. Okay. So to give you an example on that, say for example, if these are two matrices, A is equals to 2 1 minus 7 4 minus 1 minus 2 8 and 5 1 minus 4 10 and minus 7 minus 6 3 3 0 8 minus 2 minus 10 4, and B is equals to 1 0 0 0 minus 2 minus 4 3 minus 2 3 9 minus 12 12 0 0 0 0 0 0 0 0. Okay, now these matrices are row equivalent. These are row equivalent matrices A and B. So first of all, we have to find the rank of A and dimension of null of A, right? So we can see here the rank here is of this we have to look for the number of pivot columns. So in this case, number of pivot columns is only 2, so it means rank of A is nothing but equals to 2. And you can see the dimension of null of A, because rank plus dimension of null A should be equals to n, which is 4 cross 5. So n here is equals to 5. So dimension of null of A is 3, right? So dimension of null of A is equals to 3, right? Now the second one is second question is find the basis for column space of A and row space of A, right? So the basis you can easily find for the column space of A is nothing but equals to the pivot columns here. So pivot columns is first 1 and 2, so we can pick the first two here, which is 2 1 minus 7 4 minus 1 2 minus 2 8 and 5. These are the bases of column space of A, right? Similarly, we can find the basis for the row space of A, and the row space of A. You can see here it becomes basis as 1 1 minus 2 minus 4 3 minus 2 and 0 3 9 minus 12 and 12. These two are actually the row basis of is a basis for row A. Okay, basis for row A. Okay. So you can use that, and remember that we've been told that we have to when A and B are row equivalent, we can use the rows in the echelon form of the vector. So B is the echelon form of matrix. B is the echelon form matrix of A. So we can use the following vectors of B to represent the row space of A. Now similarly, third question is, so So if the question is how we can find what is the next step to perform to find a basis for null A. Okay, now the thing is, for null A you have to perform what you have to do is to bring B matrix to reduced echelon form, and then you have to basically do the process which we covered in this example. So what we did, we reduce into reduced echelon form and write those equations in a form like that, from where we can actually find the basis vectors for the null space of A. Okay. And the last question is that how many pivot columns are in row echelon form of A transpose. Okay, so how many pivot columns are in a row echelon form of A? So because you know that rank of A transpose is rank of A, right? And we know that again column of A transpose is nothing but equals to row of A. So A transpose also has two pivot positions, also has two pivot positions. Okay. Now this is the end of this topic. Hopefully in the next lecture we'll talk about the change of basis in a vector space. Okay, thank you. Allah Hafiz.